Hello students, we're going to start the next chapter. This one is about applications of Newton's laws, and really what it's about is forces and different kinds of forces and then what you're going to do with those forces. So the first part of the 5 parts is about friction, and I'm going to start by showing you a little video from Hewitt regarding friction.
I'm going to pull this block along the table. And I'm going to pull it so it has no acceleration. Let's see if I can do that. Steady, steady, steady. What was the scale reading when I pulled it? 4. Let me try it again. I'm pulling against friction, isn't that true? There's friction here. It takes a lot to get it started, but once I get it going, steady, steady. What was the force when it was going?
3 newtons.
About 3? 3 newtons is registered, right? Do you know there are people who could watch that and see that it's moving with no acceleration? And they know enough physics, they can say, hey, you know what? I can calculate in my head what the friction force must have been that you were pulling against. And there are people that can't make those calculations. But there are people who can. And all they say is, honey, when you were pulling it, it took 3 newtons to keep it going. I can tell you how much the friction was, so long as it didn't accelerate. See if you're sitting next to someone who can do such a thing in their head. Go. If when I pull that, I get 3 newtons. There's 3 newtons pulling it this way. Do you guys know anyone who can calculate what the friction must be? Aren't you sitting next to someone? What's the person next to you say? How many newtons of friction?
3 newtons.
How many say 3? Yay, most everybody. That's right.
Okay, so the answer was there had to be 3 newtons of friction. Okay, so I don't want to insult your intelligence, guys, but I think it might be worthwhile to go through the logical process that leads to that conclusion. So, first thing, the acceleration, he said, was 0. All right, so we have acceleration was 0. All right, so, well, if the acceleration was 0, that means that the net force was what? All right, well, remember Newton's second law says F equals ma, and if a is 0, that means that the net force had to be 0. Okay, so now we know that the net force was 0. Now, the block was being pulled by the scale, so the scale, here I'm going to draw a free body diagram here. So here is my brick, and we've got the supporting force, or the normal force, we'll call that, and we've got gravity, call that. All right, they cancel out, so we don't have to worry about them. But we've got the scale, the spring scale pulling, right? So we'll call that, I don't know, call it F pull, and this is the 3 newtons, right? F pull is 3 newtons, and so we know that the forces have to add up to 0. So there must be another force going this way that cancels F pull. And what would that canceling force be? And so it's going to be the friction force. So F friction. And we're going to learn that there's different kinds of friction and so on. Ultimately, we're going to label this F sub K because it's K stands for kinetic. It's the kinetic friction. Okay, so we know that it was 3 newtons because of the combination of facts, that the acceleration was 0, therefore the net force was 0, therefore the pulling force had to be canceled out by something. It was being canceled out by the friction force. Okay, so sorry I had to explain all of that. I hope you didn't get bored just now, but you know, I thought it was a worthwhile thing to do. Okay, so yeah, let's get to the notes. All right, so the general rule of friction is that friction force always opposes displacement. So the direction of the friction force is always opposite to the motion. So if a car is moving to the right, for example, the friction force will be to the left. If something is falling, like a rock, and the rock is falling down, then the air friction force, the air resistance force, will be in the up direction. So the direction of friction is always opposite to the motion. Now, there are different kinds of friction. And so the brick on the board that Hewitt was just demoing in the video, that's solid against another solid, a solid-solid friction. And that breaks down into 2 subcategories. If things are moving, they were moving in the video, so we call that kinetic friction or dynamic friction. But sometimes you have a situation where you've got friction, but things are not moving. We call that a static friction situation. Besides solids, sometimes we have to deal with fluids, like airplane designers or even car designers have to deal with the flow of air over the car. And boat designers have to deal with the flow of the water under the hull. So we have fluid friction. And that actually does break down into some categories, subcategories. If the fluid moves fast, then you get this churning effect, turbulence, and that's one, the friction will behave one way in that situation compared to if the air flow or fluid flow relative to the hull or relative to the airplane or car is slow. We call that the laminar flow situation. Laminar meaning that the flow of the fluid is smooth over the surface. And then finally, there's an interesting type of friction, electromagnetic, which has some practical uses. It gets used for damping the vibration of a scale and other mechanical things. So that's one more type of friction. Okay, so let's continue with the first sort of friction that I mentioned, solid against solid friction. So to get a really good understanding, a detailed understanding is tricky, and it's sort of beyond the scope of this physics class, but I'll just say that when you've got 2 objects that are pressing against each other, the molecules, the surfaces, will form temporary chemical bonds and almost weld together. In fact, 2 very smooth pieces of metal, if they're pressed together, occasionally they will almost weld. And it's called cold welding, and it can be a big problem in factories and so on. But anyhow, what we do know is, without getting too complicated, is that the friction force is proportional to the amount of squeezing between the 2 objects. So if you have strong squeezing, you'll have more friction. If you have just a light squeezing, then there'll be just a little friction. And so here's a kind of a basic formula here. We've got that the friction force is equal to the friction coefficient, which gets the Greek letter mu. So this is the Greek letter lowercase mu. That friction coefficient times the normal force. So it's the squeezing force between the two objects. Now the friction coefficient depends on the materials, and it's not the kind of thing that you can just say, oh, I know what it is. You have to measure it. And so there are big fat books of engineering manuals and so on where they've measured, okay, this is the friction coefficient for rubber against steel, or this is steel against concrete, and so on, all these different combinations. They have to be measured. Okay, so now let's clear that. Now we, as I mentioned just a little while ago, there's friction in the moving case, the kinetic friction, and there's the friction when things are not moving. And so I'm going to write the formula that we just saw. This formula gets written twice, basically. So we write it once for the moving case, the kinetic case, and so we have F sub k, k for kinetic, equals mu sub k, the kinetic friction coefficient, times the normal force. And then in the static case, we have that the static friction is equal to the static friction coefficient times the normal force. So we have two versions of the friction formula. Now notice that there's a little extra stuff here for the static case. I wrote F sub s for static, comma, max meaning maximum. And so we're about to talk about this, but I'll just mention, that this means that the friction coefficient in the static case will be less. It could be down to 0, and then it'll go all the way up to a certain maximum amount. And when you get to the maximum account, if there's any more sideways force, the two objects suddenly get unlocked from each other, and then suddenly you're going to the kinetic case, and when that happens, this formula no longer works. You have to start to use this formula. So this is kind of messy, right? So we need to figure out how to do all of that. Okay. So let's get into some of the details of how to do that. So static case. Nothing is moving. We have equilibrium. I've got a little diagram here. The guy is going to push on this box, and then I made a little table here to explain what's happening. So if he just stands there and he doesn't push at all, then the friction force is 0, and the net force is 0. The net force is, at this point, is just gravity pulling down and the supporting force, the normal force, pushing up on the box. Now the little guy here decides to pull, and so he's pulling to the left, so that's a negative pull, and the box doesn't move. I mean, it is static, right? It's a static problem. So that means the friction force was positive 10 newtons, because we know the two frictions are going, the pull and the friction are going to cancel. The net force is still 0. Now the guy decides to push. So now he's pushing to the right. And the box doesn't move, so we know the friction force had to cancel that. So it was the opposite of positive 10, it was negative 10. The net force is still 0. Now the guy decides to push harder. It's 20 newtons of push, but it's still a static problem, and so nothing's moving, and so we know the friction force is canceling. the pushing force, so it's negative 20 to cancel positive 20. So this will keep going until the guy pushes so hard that the crate or whatever it is on the ground starts to move. And then now when that happens, we need to go to the kinetic case or dynamic case. So that gets us to here. So the guy just got it moving, let's say. And the crate is now moving. And I'm going to, yeah, okay. So, yeah, if it's moving and it's not accelerating, like the brick in Hewitt's video, then we have equilibrium. And if, on the other hand, his brick were accelerating, then it would not be equilibrium. So in the equilibrium case, the brick is going at a constant speed. In the non-equilibrium case, the brick would be going faster, faster, faster. Now, here's an interesting thing about friction. The dynamic friction coefficient is a constant. It doesn't change. I mean, if you could somehow change the weight of the brick, right, the squeezing force, then the friction would change. But the brick's not changing its weight. So the friction is not changing. So it's really different from the static case, right? In the static case, the friction is always changing. I mean, it's changing if you change the push. But here, as long as it's kinetic friction, the friction force is constant. So in this explanation here, in this little table, I'm going to make an assumption. The kinetic friction, dynamic friction, is 7.5 newtons, and the object's mass is 1 kilogram. So we'll just use those as our kind of scenario. So I'm pushing, or the little guy is pushing with 7.5 newtons. It's not accelerating. So the friction force, well, or actually I should say, pushing with 7.5, the friction force is negative 7.5. So it's negative because we're pushing to the right, and that's the positive direction. And remember, friction is always in the opposite direction. So if the brick is moving to the right, the friction is to the left. And okay, so now it's not accelerating. The net force is 0. Or I should say, the net force is 0, so it will not be accelerating. Okay, now we push a little harder, 10 newtons. The friction force stays the same. It's still 7.5 newtons, right? That's what kinetic friction does. It's a constant. So the net force is 10 plus negative 7.5. You get 2.5 newtons. So remember I said the object mass is 1 kilogram, and remember Newton's second law, A equals F net over m. So F net is 2.5. 2.5 divided by a mass of 1. Okay, so the acceleration will be 2.5 meters per second squared. We increase the push to 20 newtons. Okay, the net force is going to be 20 plus negative 7.5. It'll add up to 12.5. 12.5 newtons divided by 1 kilogram. The acceleration will be 12.5 meters per second squared. What if we did the experiment again, except now we're pulling instead of pushing? All right, so we're pulling with negative 10 newtons, right? And the friction force always been the opposite direction. Well, now it's positive. And so negative 10 plus 7.5, the net force is negative 2.5. And the acceleration will be negative 2.5 meters per second squared. Okay, so what I want to do now is I'm going to stop this and I'm going to switch to a little kind of demo using the PhET simulations.